I'm going to give one more example about matrices. I quite like matrix groups, they're quite nice. I'm going to consider 2 by 2 matrices A, B, C, D with a particular form. I'm going to consider A, B and C and D to be integers. So A, B, C and D are members of Z. Members of Z. So they can be positive or negative integers. But I'm going to put another restriction. I'm going to say that a matrix A, which equals A, B, C, D, is required, for this group at least, to have a determinant equals to 1. So I'm going to consider the set of, I'm going to consider the set of 2 by 2 integer valued matrices. Sorry, a glitch there. 2 by 2 integer matrices A, B, C, D with A, D minus B, C equal 1. So I'll give you an example of that. If I say that's 3 and 8, no, that's a bad example, isn't it? That's going to have a determinant of minus 1. I was going to put, because 3 8s are 24, I was going to put 5 and 5 there, but that would be a determinant of minus 1. I'll tell you what, how about this one? 5, 5, 8, 3. Haha. There we go. So that won't do because its determinant is minus 1, but this will, because if A equals that, then the determinant of A equals 25, because it's 5 5s, minus 24 equals 1. Haha. Okay. So, and this is under regular, that's the set. The operation, the group operation I'm going to consider is matrix multiplication. Just normal matrix multiplication. Okay. Okay. So we've got the 4 axioms, we've got closure, we've got neutral or identity element, we've got inverse and associativity. Blom, 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 blom. Okay, closure, that's an interesting one. So let me write my group G, comma, dot. So I'm asserting that if, oh no, I've used lowercase. Let's say matrices X and Y are in my ground set G. Then I'm going to have to put XY is a member of G. I need to check that. Well, let's have a think about this. What I mean is X and Y are integer valued matrices. Integer valued matrices with unit determinant. So is the product this type of matrix, or is it something else? Well, integer valued, well, it's going to be integer valued. If I write X as equal to A, B, C, D, and then write, that's X there, and then Y is A, B, C, D, E, F, G, H, well, that's equal to AE plus BG. This one's going to be CE plus DH. Top right is going to be AF plus BH, AF plus B, scroll a bit, H. Lower right is going to be the lower row with the right column, CF plus DH, CF plus DH. So it's clearly integers. So it's integer values. Tick. But the other condition for my group G was that the determinant was a unit determinant. And you will remember from matrix algebra that the determinant of xy equals the determinant of x times the determinant of y, which equals 1 times 1. Why is it 1 times 1? Because x and y are by design or by assumption in the group, in the ground set of the group at least, and they have determinant 1. So this one is in the group as well, so it's got determinant 1 as well. And 1 times 1 is 1. So xy is not only integer valued, but it's also got determinant 1. So that's closure satisfied. Where's my, there it is, tick. Neutral element, well, we've got a neutral element, we've always got a neutral element. It's A, B, C, D, that's the general element in the group, times 1, 0, 0, 1. And of course you just go through the motions and it's A, B, C, D, check. Actually, there's something I've forgotten to check. I've got to check that the element I'm presenting as a neutral element is in fact in the group. And it is in the group because it's integer valued. Yeah. And the determinant equals 1 times 1 minus 0 times 0 equals 1. Check. So it's just as well. Yes, it's all very well having a neutral element, but we've got to check that the neutral element is a member of the group, and it is. What about inverse? Well, you'll remember that in the general case, A, B, C, D for any values to the minus 1, this is just normal matrix inversion, equals 1 over A, D minus B, C, and then it's D, A minus B minus C from just elementary matrix theory. So let me write out the entries of my inverse element a little bit more better. It's going to be D over AD minus BC for this one. This one's going to be minus B over AD minus BC. This one's going to be minus C over AD minus BC, and this one's going to be A over AD minus BC. You can check that it's an inverse just by multiplying it out yourself. I'm just checking it myself now. I've just got to make sure. Now the crucial observation is that this thing here is a member of the group because it's got two things. Firstly, it's integer valued. It's integer valued, it doesn't look integer valued, but you've got to remember that AD minus BC equals 1 in this case, because that was one of the conditions for being in the group, that the determinant was equal to 1. So I'm just dividing by 1. So I can rewrite that as D minus B minus C A, and just divide by 1. So it's integer valued, and of course it's also got unit determinant. So, because the determinant of this, of course, is AD minus BC. Actually, it's AD minus B times minus C, because the signs have changed, which is, of course, AD minus BC, which equals 1, because this element was in the group. So we're checking that any element that's in the group, the inverse is in the group. So that checks out as well. Where's my list? Where's my list? Where's my list? Oh, here it is. Neutral, done it, that's that. Inverse, done it, that was just the matrix inverse, which the hard bit was verifying that the matrix inverse was still a member of this group, so checking that the inverse was integer valued and also had unit determinant, which of course is not true if we took a peculiar determinant. We couldn't say determinant equals 2, for example. And matrix multiplication is known to be associative, so that checks out. So this is in fact a group. Integer valued matrices, or at least 2 by 2 integer valued matrices, with unit determinant. And that's a nice example of a group. It's discrete because it's integers, there's no continuous real numbers or anything there, but it's nevertheless infinitely large. Very, very useful and interesting group in many areas of mathematics that. I'm going to stop there.